Okay, so we have been looking at the so-called large-scale balances. We derived small Rossby number flows. We looked at Taylor-Proudman theorem, geostrophy, thermal winds, and we looked at the zonal mean meridional sections of winds and temperature, and we said they look like they are in various large-scale balances that we were talking about. But when we say general circulation of the atmosphere or the ocean, we have to get real. We have to start explaining things that actually are observed, not just their approximate balances, right? So there are details, but we will take one approach that is specific to this book. You will see that if you pick another book like Holton, which is an excellent book as well, it goes through the equations and it derives actually the meridional circulation, including vorticity, potential vorticity, eddy fluxes, and so on. Whereas this book takes a more physics-based approach instead of going into the detailed equations, and goes into a energy approach. So it comes down to basically defining something called available potential energy and how it gets transferred into kinetic energy. Okay, so available potential energy is something that's locked up, and there are processes that can release this available potential energy, which then goes into kinetic energy, which means the winds and ocean currents, etc. Right? So we'll start with what we have already seen. This is our meridional section again. So we already said that the low latitudes have an energy gain, right? Remember our sphere, more energy per unit area in the low latitudes, less energy per unit area at high latitudes, and then you add energy loss as outgoing long wave, and we saw that there is net energy gain at low latitudes and the net energy loss at high latitudes. And the only way to keep the higher latitudes getting colder and colder from energy loss and the low latitudes from getting warmer and warmer from the energy gain, we have to move energy, right? So there is an implied energy transport, and we derived it for annual mean as some 6 petawatts. We will come back to this number again. We haven't explicitly said that, but we have implied that there is also a momentum budget that we have to look at. So there is a gain of angular momentum at low latitudes, and there is a loss of this angular momentum at high latitudes. Angular momentum has to be balanced, right? Otherwise the Earth will start wobbling. Because it's basically torque, right? They have easterly winds in low latitudes, westerly winds in high latitudes. Unless the angular momentum is balanced, you will get a wobbling, and the length of day will not be constant. And this does happen, for example, when large-scale phenomenon like El Nino move the angular momentum, they perturb the angular momentum, you get small changes in length of day. We will see that later on. Okay, this is the broad idea, and you remember the Hadley cell we talked about with easterlies in low latitudes and westerlies in high latitudes. We'll see more details about exactly how angular momentum is being picked up and transported northward. So there has to be an energy transport, there has to be an implied angular momentum transport, which is conserved. Energy has to be conserved because we are constantly moving energy from energy excess to energy deficit areas. It turns out that angular momentum is not that simple. Okay, so angular momentum and transport conservation can be seen with this figure we have seen before. This is the zonally averaged annual mean sea level pressure. So we have low pressure in the tropics, warm air, low pressure, rising air, deep convection, etc. We had subsidence and high pressure in the subtropical gyres, the subtropical highs. we call it the gyres in the ocean and the highs in the atmosphere. Low pressures in mid-latitudes, the subpolar lows. Okay. Corresponding to that, we had argued that you can look at the geostrophic kind of balance and add Coriolis and get the easterlies and the westerlies corresponding to these pressure gradients. Obviously, there is friction near the surface, and we said convergence and divergence is happening because of the meridional winds. Okay, so the trick here will be to say, we keep saying westerlies being so dominant, and you can see the difference in magnitudes as well. Generally, meridional winds are much weaker all the way through the atmosphere. And we keep saying there is energy transport required from low latitudes to high latitudes. So if the winds are predominantly zonal, how on earth are you moving energy to the poles? This is what brings together the energy transport and the angular momentum. Okay, we'll see that in actuality, day-to-day flows or short-term averages hardly show you a mean westerly winds. There are always eddies that we looked at before. Okay, these are the kind of tricky things we have to go through. So how do we accomplish meridional transport? That's going to be the key. Okay, this energy balance again in the zonal mean, annual mean, meridional sense we had seen before. We said absorbed solar looks like this, with some asymmetries in the northern and southern hemispheres. We had talked about why there is a little minimum here, deep convection and the clouds, especially obvious in the outgoing long wave radiation, because the cloud top temperatures get pretty cold, right? So it's amazing that the maximum in OLR is actually off the deep tropics, not in the deep tropics. So the net radiation is that there is a gain up to some latitudes starting from the equator, and then there is a net loss beyond some latitudes. The implied meridional energy transport needed to balance this energy gradient was 6 petawatts, 6 petawatts, 10 to the 15 watts. These are estimated, by the way. These are they take the top of the atmosphere energy measurements from satellites. Especially when you want to add the ocean and the atmosphere together, you will need other constraints on how to provide the details of the energy transport by the atmosphere and by the ocean. Okay, so there is a symmetric energy transport towards the poles in both hemispheres to balance this net energy gain and loss, energy gradient. Nature does not like energy gradients, right? So it wants to flatten them out by moving energy. Okay. This is a schematic now, adding a little bit more detail. So by opening up the zonal mean, we begin to see a few details. Okay, what is it? We had our Hadley cell, which we already talked about. Remember, starting with Hadley himself, arguing that there is one cell going all the way to the pole and back. We already argued that that's not going to be the real situation. So there is some latitude at which Hadley cell terminates above the subtropical highs, where subsidence happens. There is divergence, which means there is another cell, and then there is another cell towards the poles. We had mentioned the Hadley cell, Ferrel cell, and the polar cells, and we had also seen a zonal mean meridional cell streamlines, which showed that the mean circulation was very weak at higher latitudes. That is related to the issue of how to transport energies from beyond the Hadley cell. Hadley cell is obviously doing a direct energy transfer, right? Whereas beyond that, we are not showing any cells here. We're showing strong westerlies in the upper atmosphere, and the westerlies extending almost all the way towards the poles. There are very weak polar easterlies which are not even shown here, right? The polar cell, we said, was related to having high pressure, air flowing out, adding Coriolis and creating easterlies, polar easterlies, right? So there is northeasterly and southeasterly trade winds in the deep tropics that Hadley also had seen, and he had already figured out the impact of the rotation of Earth. And there are mid-latitude westerlies, but now we are saying there are also eddies. Okay, you can see there is cyclonic circulation on this end, there is anticyclonic circulation on this end, and there is this meandering of the westerlies. So we are not talking about steady westerlies anymore. Okay, that's where the eddy fluxes and so on come in. The animation of the aerosol transport we saw, for example, which we will see again, showed these, and the satellite image we had seen in the very first chapter, showed these typical southwest northeast tilting bands of transport in the northern hemisphere, and the other way, southwest north east tilt in the southern hemisphere. So those come from the way the energy gets transported across these. Angular momentum is also transported, but we'll see that it's not necessarily conserved. There are instabilities in the system as you move a ring of air from the low latitudes to high latitudes. Energy momentum begins to break down. Angular momentum is not conserved anymore. We get something called baroclinic instabilities, and they move in certain ways that they make a net transport of energy despite having no strong meridional winds or very steady zonal winds. Okay, very interesting stuff. We will not go into too many equations, but you need to get a sense of the energy arguments that are involved. That's critical, because you can then go back to a book like Holton and look at the equations, and they will make much more sense.